Welcome to the Laboratory of Advanced Membrane Separation Processes. Today, we're diving into an exciting experiment that demonstrates the principles of nanofiltration. Our goal? To understand how nanofiltration, a powerful membrane technology, can soften tap water sourced from the river Les near Montpellier. This process removes hardness-causing ions, like calcium and magnesium, to produce cleaner, softer water for a variety of uses. As a first step, we place the membrane module into its holder and screw it in. Using a socket wrench, we make sure that it's secured. This is where the permeate will flow out of the membrane and into our beaker. Then, we start filling the tank with the tap water we want to filter. First, we turn on the system by setting the main switch to position 1. We verified that the drive display lights up to confirm the system is receiving power. We start collecting the filtered water in a big beaker at different pressures. Then, we weigh the mass of the water with a precision balance in order to measure the flow rates. We repeated the experiment twice for each pressure measurement. The last thing is that we depressurize it till it reaches 0 bar. We switch it off. Finally, we clear out any residual water left inside and take the membrane out. With that, our nanofiltration process comes to an end. Here are the calculations for the volumetric flow rate for the following pressures: 8, 10, 12, and 14 bars. And we can notice that the permeate flow rates and flux increase with increasing pressure. This is a visual representation of the previous conclusion. Now, it's time to analyze the water quality. In this step, we'll measure the hardness of 3 water samples using the EDTA titrometric method. We start by introducing 10 milliliters of the water sample into a 100 milliliter Erlenmeyer flask, keeping in mind that there are 3 different samples: tap water, mineral water, and filtered water. Then, we add 5 milliliters of ammonia buffer to adjust the pH to 10. This pH optimizes the complexation reaction. Next, we add a microspatula of areochrome black tea. This indicator binds with calcium and magnesium ions, creating a violet-colored complex. Now we fill the burette with a 0.01 molar EDTA solution to prepare it for the titration. After that, we introduce a magnetic stirrer to make sure the solution will be rigorously mixed and homogeneous. Then we slowly titrate with the EDTA. As EDTA binds to the calcium and magnesium ions, the indicator is released until the solution turns from violet to blue with its adding. Mineral water's hardness reflects its natural mineral composition and is appropriate for what you would expect from this type of water. Tap water has the highest hardness and mineral content, indicating it may require softening for certain applications. And finally, filtration is effective in reducing water hardness by decreasing the levels of calcium and magnesium, but the water still falls in the medium-hard category. And finally, in this last section of the we'll measure the water conductivity using a conductivity meter, focusing on the same 3 samples to wrap up our analysis. For the measurement of the water conductivity, we start measuring approximately 90 milliliter of water to gauge a round bottom flask with 10 milliliter of a KCl solution at 0.1 molar. To prepare 100 milliliter of KCl at 0.01 molar. Once diluted, the result will be a solution that serves as a reference solution for calibration. So first, we transfer the solution into a flask. And then we calibrate the equipment introducing the electrode of the conductivity meter in the KCl solution we made. Here we obtain a reference value of 1,319 microsiemens per centimeter. After that, we rinse carefully the electrode, and we repeat the process with the different samples. So, for mineral water, we obtain a value of 454 microsiemens per centimeter. For tap water, a value of 777 microsiemens per centimeter. And for filtered tap water, a value of 483 microsiemens per centimeter. Mineral water has moderate and the least conductivity. Tap water has the highest conductivity, reflecting high ion concentration. Permeate water, slightly higher than mineral water, but significantly lower than tap water. Basically, conductivity correlates with ion concentrations. Tap water's higher hardness is supported by its higher conductivity, while permeate water has lower ion content due to filtration. This work was done by the following members. It was supported by University of Montpellier,